All right, here we have that x is normally distributed, mean 0, variance 1. Y is equal to x to the 4th. Find P, D, F for Y. Go ahead, start working on it. By the way, we're now moving into material that's a little bit more technical, a little bit more difficult. Expect many quizzes. Expect many quizzes based on homework from yesterday on. Okay? All right. This one right here is actually worked out, or close to worked out with notes and close. And it's done exactly the same way. That's what I'm erasing. And that is, I want to find the probability that y is less than or equal to t. This is equal to, I'm putting in y's other name. This is the probability that 0 is less than x to the 4th is less than or equal to t. Now, I have to solve for x because that's the only thing I really know. It is a normal distribution with mean 0, variance 1. And so therefore, solving for x, I have that it's a probability of t to the minus 1/4, t to the 1/4 and a minus in front, is less than x, is less than t to the 1/4. Any questions on that? Okay. And this right here is equal to 1 over root 2 pi, the integral from minus t to the 1/4 power to t to the 1/4 power e to the minus x squared over 2 dx. Yes?
If we separated the probability with the two inequalities,
Sure, that's fine.
that's fine.
That's fine. You should get, and then you add it together. That's fine. That's perfectly fine. As long as you get the right answer.
Yeah.
Okay, good. So you see his confidence? He already knows he's got the right answer. Okay. And so now I want to find the derivative with respect to t of the probability that y is less than or equal to t. And this is going to be just differentiating this integral. So it's going to be 1 over root 2 pi e, the upper limit, this is chain rule, upper limit will e to the minus t to the 1/4 quantity squared over 2 times the derivative of this, which will be 1/4 t to the minus 3/4. And then now I take the lower limit, that's going to be minus e to the minus t to the 1/4 power squared over 2 times the derivative of this, which is going to be minus 1/4 t to the minus 3/4. You left it in that form, that's fine. If you collected terms, you probably made it arithmetic error. Did you? So, but if you got that far, it'll be said, yeah, you got that. Okay, any questions? Yeah?
Instead of t, what if I kept it as y?
I beg your pardon?
If I kept the t's as y, like if I changed the variable, is that okay?
How if you change variables as long as you got the right answer? I mean, there's probably only about 50, 60 ways to do this problem. And so we're mainly interested, I mean, as you know from the test, what we're interested in is what you know, not if you can add or subtract. And so it'll be graded in terms of, does he know what he's doing? Okay? In your case, it is. In her case, does she know what she's doing? Oh, you didn't? Okay. All right. So that's that. Any questions on this? Okay. Now, got the new notes. And I'm going to be expanding them a little bit when I have a chance this weekend. But I want you to pay attention to the following thing. We started off, let's see if I can find another marker. We started off the Taylor series early on. So if I have f of s t equals f of s plus a change in s, f of s plus the change in s, t plus the change in t. We know from Taylor series that this right here is going to equal f of st plus the first partial of f with respect to s times the change in s plus the first partial with respect to t times the change in t plus other terms. That just comes from Taylor series. All right. So what we have is a new pen in a second. So what we have, it's this right here. Well, I thought I had a pen. I got a broken pen now. Oh boy. So we got to find a different pen. Let's try this one. So what we have is, when I take this on this side, we have the change in f is equal to the partial of f with respect to s, the change in s, plus the partial of f with respect to t, the change in t. Okay, everybody see that?
What does it say all the way on the left?
Can't hear you.
What does it say all the way on the left, on the top? The first term?
First term, the first term is f. If I start with f of st, and I'm going to change s by delta s, and I'm going to change t by delta t. Okay, that's going to equal f of st by the Taylor series. These are the first terms. And so what we have then is this relationship right here. And this is an important relationship which is used a lot, considerably, everywhere. Now what do is often we just simply say, let's let the first term, the partial of f with respect to s, hey, maybe that's a constant for a while. So that's where we get the constant terms. And so what we have to expect is, I'm going to try to find another darker pen now. I don't like that. I've gone through just about every colored pen I can find. So what we have then is, quite frankly, it's that, oh, this is good. The change in s is equal to mu s, the change in t plus mu s, the change, mu sigma s, the change in x. That this right here is very, very natural. It really comes from Taylor series. It's a first approximation for what's going on. It's a first approximation for what's going on. Therefore, you have to expect this equation to crop up almost everywhere. you have to expect this equation right here. Delta S is equal to mu S delta T plus S sigma S delta X to crop up, where we found out now that delta X, to make sense, really has to be normally distributed delta T variance. We have to expect this equation to crop up in physics, medical problems, in economics, finance, everywhere. Because it's such a fundamental, it's just the first part of a Taylor series expansion of a more complicated type problem. All right. That means that we want to know, how does S change? Now, this problem right here is called scale-free often. It's called scale-free. And really, what I'm putting down here, you know, the first part of the lecture today, is really directed to point out that what we did last time. You have a question? You have a question? Yeah? Okay. That what happens is that the material that we developed last time carries over to almost all disciplines. That we're doing it in economics, finance, but it carries over to almost everything else. So let's look at that equation, and let's let U be equal to 10 to the 6th S. Whoa! It really expands everything very, very large. So S might be this big, and U is huge. Talking about something with a very, very different scale. And so what is the change in U? The change in U is equal to 10 to the 6th, the change in S. So let's try to find what happens here in this equation right here when I put in U. And here I'm going to have the change in U. And then what is going to be S? Well, U is going to be 10 to the 6th S. And so when I find the equation for delta U, I get the same equation. I get the same equation because the 10 to the 6th cancels out on both sides. The 10 to the 6th cancels out on both sides. And so it's scale-free that I get this equation for looking at really micro-type things. And I get the same equation looking for huge, huge scale things. And in any problem, any area where this is a reasonable approximation, where surface area of something like here is changing depending on what the current surface area is, delta T plus indeed a random type term. Oh, I got a mole right here, and the mole is going to be increasing. How's the size of the mole increase? Well, I don't have a mole, but it's increasing depending on what on each little increment. So it depends on the current size of the mole on all the sides, and then the random effect. So just about anywhere you are, you're going to run into this equation. All right, that means it is crucial that you review the notes to understand what happens to find what is the probability distribution for S of t. You need to know this, you need to know how to derive it, hint, hint, hint. You need to know all of that. What we did is we used Ito's lemma, where we chose f of s is equal to the natural log of s. I was asked at the extra session we had on Friday, yesterday meaning Tuesday, that where in the world did you get the natural log of S? Well, what happens if I try to simplify this by dividing by S, the way we found the value of money? If I try to simplify this by dividing by S, I get delta S over S equals mu delta T plus sigma delta X. And this sure looks like it came from the natural log of S. This sure looks like it came from the natural log of S. So that's why we said let f of S equal to this. Then we use Ito's lemma. To find delta natural log of S. So delta natural log of S will not equal this when I use Ito's lemma. It will equal another term, the 1/2 sigma squared S squared delta S squared. And so what we do is we're going to find this right here. We add them all up. This is all in your notes from last time. Your notes are not complete. What you do is you just take a look at the notes that I sent out yesterday, and it's all listed there. You just add all of the little increments. So what is that? That's going to be, here is T. What is delta of natural log of S in this interval? It is natural log of S of T1 minus natural log of S of T0. That's going to be the change in the natural log. And then what we do is we write what's on the other side from Ito's lemma. We write that down. We then say what's going to be the change in the delta S right here. You add that in. That's going to be the natural log of S of T2 minus the natural log of S of T1 equal whatever the right-hand side is, and we go all the way down. And there turns out to be a magical cancellation. And so what we end up with then is let's see if this one works. What we end up with then is the magical type statement that natural log of S of T, by just going through that summation, it's in your notes and the notes which have been passed out, is going to equal the natural log of S of T0 plus mu minus 1/2 sigma squared T minus T plus W where W is normally distributed, mean 0, and variance sigma squared T minus T. So we've got that elusive, or at least a form of that elusive. What is the likelihood of S of T? You're in medical school. You want to know how is that cancer changing? What's the likelihood the cancer is going to do such and such? Here's the type of equation you probably would use. Okay? And so what we want to do is we want to find what is the likelihood of S of T. So let's define the probability of S of T less than or equal to S. That means I have to write this as the probability of the natural log of S of t is less than or equal to the natural log of S. And you know what the probability distribution is for the natural log of S. It's a normal distribution with the mean given by, so probability distribution with the mean given by this, and variance given by this. So this gives you a wonderful way of being able to get predictions. Just think. Suppose. What happens is, you got an iPad. You got an iPad. And what happens is you're going to, what is going to be the price of an iPad on March 14th? Okay, you know the current price of an iPad on the market, on the free market or something like that. So what you do is you go through this right here to find what is going to be the price of the iPad. You can't find the precise price. But you find the probability that it's going to range between, on the free market, between 350 and 450. High probability, you say, or low probability, I'll sell mine and buy one later on. So that gives you information about what to do. So therefore, what we have is, by knowing what this thing right here is, by finding the PDF for this, you can solve a lot of problems. This is a homework problem. I'm not going to solve it for you. I'm going to expect you to solve it. I think that's a strong hint of what to expect. But I will give you the answer. I will give you the answer. If y equals sigma x, did that wrong. If the natural log of y is distributed with mean mu, that'll be that ugly term over there, and sigma squared variance, that's going to be this ugly term right here. You will find when you go through this computation that the PDF is, well, let's first write down what would be the PDF for this. The PDF for this would be 1 over root 2 pi e to the minus x minus mu squared over sigma squared 1/2, right? That's the mean for the normal distribution. We've carried that up in class. What it will be here, it'll be 1 over root 2 pi, keeps that, e, keeps that, to the minus 1/2. Place of x, we write down the natural log of s, minus mu over sigma squared times 1 over s for s greater than 0. That will be your answer. So in other words, all I'm doing is replacing the x with the natural log of s, and then putting the derivative of the natural log of s in the front.
Are we missing a sigma in the...
I can't hear you.
Are we missing a sigma in the square root? Of
Yes, we surely are. I just did that to make sure that you caught it. Okay. And she says, hey, you left out a sigma. You've got to have a sigma here, and I have to have a sigma here. Thank you. That gives you a better answer. Okay. Now let me show you how this is. A question? You got a question? No, go ahead. Usually when people have a question, it's something that 5 other people want to know. Okay. So here I have, if the natural log of y is normally distributed, mu sigma, then the PDF for y, probability distribution function for y, is 1 over s, 1 over root 2 pi, sigma, got my hand slapped, I forgot that first, e to the minus 1/2 natural log of s minus mu over sigma quantity squared, where sigma greater than 0. Yeah.
Sigma is outside of the root, right?
Yeah. And he wanted to know is sigma outside the root, and it surely is. So let's make double sure that we know this by putting on another parenthesis. How does that sound? Got it? Good. Okay. Now, we're going to show you how. I'm going to show you another relationship. See, what this does is it says that this log normal distribution is closely related to the normal distribution. This log normal distribution is closely related to the normal distribution. So it's going to look, when I look at the curve, the bell-shaped curve, it's going to look a little bit warped and squashed and everything else. We're going to talk about that in a second. But I want to show you the close relationship between the normal distribution and the log normal distribution. And this is where that U I had earlier comes in. For the normal distribution, I know that 1 is equal to 1 over root 2 pi sigma the integral from minus infinity to infinity of e to the minus u minus mu over sigma squared to the 1/2 du. Okay, that just says you sum all of the little probabilities, you have to have probability 1. Okay, certainty. Now, you see that U in there? U stands for ugly. Okay? All the substitutions you made in calculus, you always use U for the substitution. And that's because you let U stand for the ugly part of what you're trying to get rid of. So what I'm going to do now is I'm going to ask you to use the following change of variables. Ugly is equal to the natural log of s. Go ahead. Find the change of variables and we'll see what happens here. Okay, enough of you are looking up that I figure you have that. So first, everywhere I see a U, I'm going to write in the natural log of s. Minus 1/2 natural log of s minus mu over sigma squared. Now, I have a du. So I have to find what is du. Du is equal to 1 over s ds. And so therefore, I'm going to have a 1 over s ds with the change of variables. There's two other places where x crops up. One of the places where x crops up is in the upper limit. Here, this is saying that u is approaching infinity. If u is approaching infinity, what happens to s? Yeah, it also approaches infinity, so the upper limit is infinity. The lower limit here is u is approaching minus infinity. How do I get u to go to minus infinity with s? So therefore, the lower limit here is 0. And what we do is we have then that this whole thing is equal to 1. Here is a probability distribution function. If you see, it's only a change of variable from here to here. If you take a look, it is precisely what I stated earlier will be your PDF of the log normal distribution. So this is an important distribution. It's important, does not come from the fact it's a change of variable. A lot of books say it is a change of variable, so it's important. Nonsense. Total nonsense. It is important because of this expression right here, which crops up almost everywhere. And when we wanted to find what is S of t, we know that S of t is going to be, the probability distribution, is going to be this thing right here, natural log of s minus mu, and you know what that mu is, it's that natural log of S of t 0 plus all that other terms, and you know what sigma is going to be, and you plug that in here. That's why it's important. So the log normal distribution is important because it is the natural distribution associated with delta S type terms. And that's why you will see the log normal distribution everywhere. Okay? Any questions? We got one more question and then we're going to get on to something else. The one more question is, what does it look like? What does it look like? And I'm going to leave some of this for your homework, but I'm going to give you an idea of what it looks like. The normal distribution, you know, the old bell-shaped curve, here is mu. The normal distribution looks like that. Now, if you choose a smaller sigma, the normal distribution is, well, it's going to get closer and closer to mu. Bad. You can see why I'm not an artist. Shoots up like that. Because area under the curve has to equal 1, so it's going to have a stronger peak. Now, for the log normal, I have to expect that some of this is going to be squashed in. I have to expect for the log normal, let's see if this one works. For the log normal, I know I can't go to the left of 0. I cannot go to the left of 0. Because what happens is when we went through this distribution, we had natural log of s. S is only defined when s is greater than 0. When we did this right here, we see that s goes between 0 and infinity. So s has to be to the right of 0. So what we're going to do is we're going to squeeze in all of this into a certain part of the region, and all of this into another part of the region. Take a look. Where do we think things are going to hang around? On the normal distribution, x is hanging around both sides of mu. Here, I'm expecting that the natural log of s is going to hang around mu. The natural log of s is going to hang around mu because this is symmetric, one side or the other. All right? And so I expect the natural log. So let's look at a special case of when mu is equal to 0. When mu is equal to 0, we expect s to hang around 1. Not quite. Not quite. And this is going to be your homework exercise that I'll be sending out today. The homework exercise is to find what is the peak of this. What is the peak of this probability distribution? See? What is the peak of this one right here? Well, that's easy. When I differentiate, that's a constant, I differentiate that. I'm going to get x minus mu, set that equal to 0, x is hanging around mu. Or if mu is equal to 0, x is hanging around 0, as we have from that drawing. Here you're going to find that the peak is hanging around something like about 1 over e to the sigma squared. So if sigma is getting closer and closer to 0, in other words, we're getting really, really tight, it's hanging right around 1. If sigma is larger, it's a little bit to the left. And so the probability distributions with the log normal look a little bit like this. If sigma equals 1, and then here I have, and mu equals 0, it's going to look a little bit like that. Right? Distorted. It's a distorted bell-shaped curve where I'm trying to get all of the information I have to the left over there, squeezed in here type thing, and then it's moving off there. If sigma is equal to approximately 0.25, then what happens is it looks like something like that. Okay? So the peak. Do you have a question? No, you're in front of me right there. Do you have a question? Yeah? Okay. What happens is that as sigma is closer and closer to 0, that peak point that we had here is getting closer and closer to 1. That's if mu is equal to 0, you can make the adjustments when mu is something else. When sigma is getting larger, like 1, it has a peak over here and comes down like this. So you should have some sense of what the log normal distribution looks like, because it props up so many places. Okay? Any questions? Yeah?
You could say this peak should be 1 over e to the square root of e to the power.
The sigma squared. Yeah, that isn't very clear, is it? So let me rewrite that. Green isn't very clear. 1 over, it should be something of the order of e to the sigma squared. Okay? And so when sigma is getting closer and closer to 0, e to the 0th is 1, and so therefore the peak is going to be closer and closer to 1. When sigma is equal to 5, that's e to the 25th, closer to 0. And so what you're able to do then is you have a sense. And I want you, this is one of your homework problems, is to see how far up am I on this right here, and to find what's going to be the peak of the log normal distribution. And it'll be to try to sketch the log normal distribution. I want you to know that because it's going to crop up again and again and again in finance and just about everywhere. Any questions? All right. Well, you have a question? Oh, yeah. Just moving around up quickly. Okay. Let's quickly review what we did so far today. What we did is we started off by reviewing and having a quiz on how to find PDS, probability distribution functions. That's important. You will see this again and again. Be sure you know how to do it. Secondly, what we did is we used Ito's lemma, or I didn't use Ito's lemma. I reminded you from your notes last time that if I use Ito's lemma over something like this, that I'm going to get a probability distribution function for what will be the price of the asset, what will be the price of the spread cancer in your soul, what will be the spread of radium or radioactive material or anything else. Because they all come from that kind of equation. So then what we did is I pointed out the importance of the log normal distribution, which is something that you really, truly have to have a sense for. Much like we have a pretty good sense for the bell-shaped curve, you want to have a sense for the log normal distribution. Okay? Now what we're going to do is get into a question that was asked at the extra session. And that was, by the way, I'm going to try, oh, yeah, announcement. Thursday, March 6th, next exam. Thursday, March 6th, next exam. So more than a week's advance notice. Second, I'm going to try between now and then, time permitting, to have extra sessions every week. And I'll try to schedule change the date. Now, what you did is you had in calculus problems like the following. The rate of change of f of t dt equals. What's f? What is f? Where does f come from? Where does f come from? I'm trying to slide away, huh? Where does f come from? In calculus, we have the derivative of f with respect to t. Yeah, what is f? Where did it come from? It's just there. It happens to be a problem that is a sign of whatever you're trying to look at, an issue that you're trying to look at. Maybe it is speed, maybe it is how fast is water spreading across the floor, whatever the issue you're having to be interested in analyzing. And so therefore, when we get to Ito's lemma, I was asked, where does f come from? Where does f come from? You remember what Ito's lemma happens to be. Ito's lemma happens to give you, and another obvious quiz problem is finding Ito's lemma for the different delta s's that I have. And that's on your homework. I'm sure you do know how to do those. But we know that this is equal to the partial of f with respect to s, delta s, the partial of f with respect to t, delta t, plus 1/2 sigma squared s squared, the second partial of f with respect to s, delta t. And so the question is, where does f come from? It comes from wherever you happen to be interested. So let me give you one right now. And this was actually already on your homework, but let's work out a little bit more generally. Suppose my portfolio is equal to V of S of T minus alpha of S. What's V? You were going to ask that, weren't you?
I'm gonna ask, why is the portfolio like such a function?
Why is portfolio such a function? Excellent question. What we want to do is we want to hedge. And so I'm going to have V is going to be either a put or a call. It's going to be either a put or a call or some combination. I don't care. You decide what it's going to be. But he's asking the important WAGAT question, who gives a darn? What in the world would I have a portfolio like that? All right. Excellent question, so let's take a look at it. Let's take a look at a call. If you have a call, what are you thinking about the future? Yeah, it's probably, value's going to rise. So how would I hedge? I could use a put, but I could also go short. I also could go short on the commodity. Because if I'm going to go short on the commodity, what am I thinking? That meant I borrowed the stock. I think the price is going to plummet. And what I can do then is I'll buy it at the lower price and then replace it. So what is this? This is a hedge. It's a hedge. It's a hedge between forward thinking in terms of the future, that's the call, negative thinking, that the price is going to drop, that's going short. The put would be the other way around, wouldn't it? And so therefore, this right here, this portfolio right here, is a simple portfolio. You can make more complicated ones, whatever you want to put for V. But a special case is where I just have a call minus alpha S. Or a put minus alpha S. Here alpha would probably be positive. Or negative, so I get a positive value. Okay? Does that answer your question? Okay? What I'm asking you to do right now is I'm asking you to compute delta pi of S of T. Compute it. Try it. Okay, straightforward. This is equal to this term, partial of f with respect to t, partial of pi with respect to t is going to be the partial of v with respect to s minus alpha, delta s, what we get from here, from this term right here. This term right here, there's no t's in here, explicitly, implicitly, but not explicit in here. So this is going to be the partial of v with respect to t, delta t. That's all that survives. And here I'm going to have 1/2 sigma squared s squared. I've got to take the partial of this one more time with respect to v. And I'm going to have the second partial of v with respect to S. And to make it a little bit more explicit, I'm going to have a partial of V with respect to S minus alpha times sigma S delta X plus partial of V with respect to S minus alpha mu S delta T plus a partial of V with respect to T delta T plus 1/2 sigma squared S squared, the second partial of V with respect to S. Okay. Everybody with me on that?
So where's your last delta T?
Let's see. I've got this term right here is multiplied times this, and this right here, I dropped that off, but we know what delta S is. Delta S is equal to sigma S delta X plus mu S delta T. So I multiply this coefficient, I'm going to have a sigma S delta X times that, and it's that times this right here. This right here is going to stay the same, and that's going to be right here. Did I answer your question, or I lost where you are now? Did I answer any questions on this?
For your formula, you have a very last delta T, right?
Yeah, I have a delta T at the end.
And you lost it.
Oh, I lost it. Oh! Oh my! That's crucial because I need that delta T. Thank you. I need that delta T. Now, what's the purpose of hedging? From the first day of football or games or basketball games, what's the purpose of hedging? Yeah, well, to eliminate risk in particular. To eliminate risk. An important part of hedging is to eliminate risk. I told you about my friend. He's quite wealthy. As a lawyer, you do badly in the market, and he'll go and check your portfolio to make sure that they eliminated risk, that they hedged appropriately. So hedging is, remember, insurance type thing to eliminate risk. Where is the risk in this equation? Where would you say the risk is in that equation? That last equation you got done. Aha, excellent. She's saying risk, 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 random behavior. That's random. That is risk. Notice, I didn't tell you what alpha equals. So how can I get rid of risk?
Setting alpha equal to derivative of the.
That's right. So what happens is we take, to get rid of risk, I get this coefficient to equal 0. And so this is a very important term on the market. Set alpha equal to the partial of V with respect to S. In the finance books, this is called delta. I can't use delta because I'm using deltas all over the place. But in the finance books, that's called delta. That is a variable that the people on a market managing a portfolio use constantly. Because what they do is they can compute, by looking at the market, they can compute what is the rate of change of, say, a call with respect to S, and that will tell them how much to have for alpha, how much to go long or short. Or if B is a put, the partial of P with respect to S tells me how much to go long or short. So this is one of the tools that you use on the market to try to manage risk. Okay, any questions on that? Now, is this the only way to hedge? Nah. I could just take, what are you going to do to hedge? Yeah.
Oh, if I'm just gonna bet on stuff.
Okay, well, you know, another way to hedge is to say, hey, I'm going to go short on all of this. Remember, we talked about going short on things, put the money in the bank. We've already talked about that a couple of times. Another way to hedge is to say, that let's take the money out. Let's take the money out. Put it in the bank. Does it have to be the bank? Nah. Nah. It can be whatever you want, but you're putting it in somewhere else. Take the money out, go invest it somewhere else. Maybe I'll invest it in bonds. Maybe I'll invest it in trinkets, anteater trinkets. Who knows what I'm going to invest it in. But I'm going to take the money out, and there's what's going to be the rate of change of the money if I put it in the bank. Yeah. Interest rate is R, and he's asking, what's the interest rate? And the question is that I claim, now so you're a banker. The rest of you didn't realize it. He's a banker. And he wants people to invest in his bank. So if not many people are investing in your bank, what are you going to do with your interest rate? Yeah, you're going to raise it up a little bit. Suppose a lot of people are putting money in your bank. You're going to lower it. So we come to our good friend arbitrage. Our good friend arbitrage says that the money I can make on the market, which is this, is equal to the money I get if I take it out of the market and put it in the bank. That interest rate will change. And so what do we have here? This is 0. This is 0, so we lost our drift term, so that's all I have here. And so what we end up with is the equation, partial of v with respect to t, delta t, that's that equation there, plus 1/2 sigma squared s squared, the second partial of v with respect to s is equal to r. So here's a delta change in my money. Here's change in my money by going into the interest rate. And I know they're equal because of arbitrage. You know, lower up and raise the interest rate is going to equal r. I forgot my delta t again. Is equal to r. So now let's put down what that is. That's v minus, what's alpha? Alpha is partial of v with respect to s. Delta t. Okay, you see what I did here? All I did was use Ito's lemma for a natural portfolio of going long or short with the item and with a put and call. That's all I did. So that's the first equation. Second equation is, he said he's going to take the money out of the market, put it in the bank. He doesn't want any more risk. If enough people do this, the interest rates in the bank are going to adjust. So both sides are going to equal. That's good old arbitrage. And so what we end up with is this equation here. Anyone see any cancellations? Delta t, I can factor out delta t. I can factor out delta t. If I factor out delta t, I'm going to have 1/2 sigma squared s squared, second partial of v with respect to s, that's this term right here. Then I'm going to have plus r s, partial of v with respect to s. So I brought all the delta t's premiums on this side right here. minus RV plus the partial of V with respect to t equals 0. Did I do that right? RV, that looks right. That looks right. Looks like a nice partial differential equation. And if you had discovered that, you would have got a Nobel Prize. That's the Blac-Scholes equation. That is the Blac-Scholes equation. That's all there is to it. See how easy it is to derive? The derivation of the Blac-Scholes equation is to simply state that my portfolio that I want to have is going to be B minus alpha S. Find my equals lemma. What is that? Get rid of risk. That's hedging. Get rid of risk. That gets rid of this term and this term. And saying that, well, wait a minute, I can also take the money out of the market, put it in the bank, set the two equal, because arbitrage is going to allow you to set them equal. Divide by delta t, and whammo, the equation you have is that famous Blac-Scholes equation that you've heard about for a long time. That's all it takes. We're going to learn how to derive all sorts of variants of the Blac-Scholes equation. You can throw all sorts of things in. Got a long weekend coming up. Have a good time. It's going to be wonderful weather. Have a good time.